Another lecture in the series of transducers, ultrasound transducers, also known as probes, scan heads, or scanners. This series discussing the basic components of the transducers, the non-imaging transducers, and imaging transducers. And here in this part, we're discussing the imaging transducers, and we have the mechanical and annular array, one group, array 1D transducers like the phase array, linear array, curvilinear, and tightly curved array. And the array 1.5 or 1.5D transducers. Also array 2D transducers. And lastly, we'll discuss the 3D and 4D imaging transducers or techniques. So again, for the imaging transducers, we finished the mechanical and the annular phase array. We also come to the family of 1D transducers or 1D array transducers, and we have some members in this family. First is the phase array, second and third are the linear and the curvilinear, and fourthly we have the tightly curved or what usually called the endovaginal probe. So a little introduction about the 1D again. Okay, 1D is when we have the PCT is cut in one direction of cutting, so it goes like this. So these are the elements in this active element PCT. So again, cutting here is in one direction, so that's why you call this what? 1D. So 1D, one direction of cutting. Okay, it's different from the 1.5D or 2D because we have again some other cutting in the other direction. So in the 1D and the 1.5D or 2D, we have different cutting directions. That's why we have the 1D or 1.5D transducers. Okay, so again for the 1D transducer, we have the phase array and we have the linear and curvilinear. Linear and curvilinear are gathered together in one study. So what are these linear and curvilinear probe? The linear is the one that we usually use it for superficial scanning, small parts, or vascular scanning. So this is the linear array. And the curvilinear, so this is here the linear, okay? And the curvilinear, this is the one usually used for abdomen scanning, okay? OBGYN. So as we see here, we have two different applications, two different shapes, but they are having the same inside the transducer, they are having the same pattern of arrangement of the active elements. That's why they are grouped together. So if I'm talking about the linear and curvilinear, the linear probe is sometimes called the linear segmental or linear sequential or linear switch probe. Okay, why you call it linear? Because the active elements are arranged in one straight line. How about the curvilinear? Again, curvilinear is called curvilinear segmental, curvilinear sequential, or curvilinear switch. Why? Because they're having the same pattern of cutting and arrangement of the active elements. Okay, and that's why because it's curvilinear, it had this curved pattern. Okay, so it's a curved line, sometimes called convex probe because of this arrangement also, or the curved probe. So all of these are discussing the outer shape. So the outer shape here is linear or curvilinear. This is the outer shape. But when it comes to the actual active elements, okay, they are having almost the same number of arrangement or the same number of PCTs. All right. So these are the active elements here. We have like ranging between 256 to 512 or the same like here. So we have here different patterns of or different numbers of active elements based on the size and the manufacturer. They are in the linear probe. They are arranged in a straight line. Okay, and they are grouped in segments. So each segment usually between 7 up to 20 actually 20 active elements are grouped together in one segment. So we have here one segment, 2, 3, 4, 5. So as we go over the face of the transducer, you can notice that they are divided into segments. Okay, sometimes these segments are activated in a sequence. That's why sometimes called the sequential. So this is here segmental because it's divided into segments. Sequential or switched based on the pattern of activation. So we have sequential, means this segment is activated and then will stop, and the next one will finish, and the next one will take over and then will finish, and then the third one will take over and then finish. So they are going in sequence. So this sequence of activation, that's why we call it sequential, or sometimes called switch because activity is in a switch pattern. So I'm explaining why we have these different names, but in general they are called the linear array. When it comes to the curvilinear, it's having the same pattern of segmentation. So we have here segmentation again between 10 or 7 up to 20 elements in each segment. Okay, and when the difference here, this is in a curved pattern, and they are of low frequency elements. This one is a straight line, okay, and they are having a high frequency probe or elements. So we have here high frequency elements and they are straight. Here we have lower frequency elements and they are in a curved pattern. So now, as we mentioned earlier, they are called sequential or segmental or switch. Okay, why? Because of the activity or the pattern of activity. Activity here in the what we call the steering is electronic. Yes, it is electronic, but not electronic via phasing like the phase array. Phase array is electronic steering and by pattern of phasing, the minute time delays or minute phase delays. So I'm talking about the phase array. But now in this pattern here is electronic but via sequencing. So it is electronic, yes, it is electronic steering, but via sequencing. What does it mean sequencing? That each group of the elements here, it has its own pulse, its own pattern of pulses, electric pulses or spikes, and they are activating this group only that will send a straight line sound pulse. And after finishing this, the next group will take over. So I'm having here the next group and the third and the fourth. So we have as many as segments here, as many as we have scan lines. All right. So scan lines sometimes are produced in some transducers by what we call the overlapping. So for example, active elements number 1 till 10 will get the first scan line, and then number 5 till 15 will get another scan line. So there is some pattern of overlapping. It's not important to know this fact, but this is just to increase the number of scan lines. So sometimes the active elements, they are overlapping in their pattern of switching. Anyway, so this is called segmental or switching or sequential. So again, each scan line is formed by what? A group of elements, and this group of elements is, or the subset of elements, this is the one that is responsible for this scan line, and then another group will be responsible for the next scan line, right? So this is what we call sequencing. Steering by what? Electronic and electronic sequencing, right? So each segment is fired separately in a vertical direction. So getting here, the scan line will go out straight line perpendicular to this face, right? So this is here in the linear array. How about the curvilinear? It's the same pattern. Everything is the same. Sequencing and groups of elements, and this group will be responsible for each scan line. But what happened here? Because the scan line is cutting or coming out from the surface of the probe perpendicular to the surface of the probe. So at this point here, perpendicular line will go this way. At this point, the perpendicular line will go this way. So this one, and that's why you get what you call the active elements here are fanning away. So they are fanning, coming out in a pattern that is not a straight line. They are not parallel. They are coming out in fan direction. So we have the far field is wider than the near field. Right. So again, the curvilinear array is having the active elements in groups, and it is activated in a sequential pattern. Okay, so electronic steering by sequencing. This applies for both the linear and the curvilinear probes. Now we come to the focusing. Focusing again is the same. Okay, and that's why I told you they are both these transducers are grouped in the discussion together. They are not the same, but in discussion they are very similar in the activities inside. Okay, so what happens here? The linear and the curvilinear, the focusing is electronic. Electronic by what? Phasing now. So there is here minute time delays. The beamformer will send the active elements. Each group will send this active element, or this group of active elements will send group of spikes or group of electric voltages in the form of a curvature. And this curvature will send, when they activate the group, this group will send the sound pulse coming out from this group that will be focused in a certain level. So if we send the next pulse from the same group with a different curvature, I will get another focal point along the same scan line, but in a different level. So I'm having here multiple focal points. So multiple focal points can be achieved via the phasing or the electronic focusing via phasing. This is for what? For the lateral resolution. So again, this is here focusing for the lateral resolution is achieved by what? Both the linear and the curvilinear. Both are achieved by what? Electronic. Okay, electronic focusing via phasing. Okay, via phasing. So this phasing will achieve multiple focal points, and again they are adjustable. I can make them shallower or deeper. I can get like 3, 5, whatever the number of focal points. I can make them shallower or deeper. So this is multiple and adjustable. Now we come to the elevation resolution. Elevation resolution, it needs focusing. Okay, and again focusing here as like all the 1D transducers, 1D family of transducers, 1D array transducers, okay? The family of 1D array transducers, they are focused in the elevation resolution mechanically. Mechanically by what? Again, the same pattern that we discussed with the phase array, we'll discuss it here because both are in the same family of 1D transducers. So 1D transducers, the elevation resolution is focused via mechanical focusing. Mechanical focusing means what? I get either an active, acoustic lens or cutting the PZTs in this curved pattern. These two different ways that will bring me mechanical focusing for the elevation resolution with a certain level of a focus. So I cannot get multiple focal points for the elevation, and it's only fixed in position. I cannot make it shallower. I cannot make it deeper. I cannot make them more than one. It's only single focus that is in the same position. I cannot change the position. It's non-adjustable. All right. So this is here the mechanical focusing for the elevation resolution in the 1D transducer, not only the linear or the curvilinear or the phase array. Even when you come to the endovaginal probe, which is the tightly curved probe, again elevation resolution is focused mechanically. Image shape. This is here something that is interesting to know. Okay, for the linear array and the curvilinear, they are different in image shape. Why? Because the face of the probe is different. The face of the probe here in the linear array is a straight line. That's why the beam, the ultrasound beams are coming out in a straight perpendicular line, and that's why I get an image what is called the rectangular image, like this one. Pattern A, rectangular image. Okay, what is the characteristic of the rectangular image? Rectangular image is having the width of the image from this end to this end. Okay, if I put here a line with this red color here, from here to here is the same as from here to here. right? So they are having the same width, shallow or deep, shallow, shallow part, or the near field, or the deep field, or the far field, right? Both are having the same width. What is this width? Is exactly the same width as the active element. So the active elements in the transducers, the face of the transducer, this will determine how wide is the element, or how wide is the image from the shallow or deeper images, okay, or the deeper part of the image. So this is a rectangular image. But also, the linear array can bring me what you call the trapezoid image. Okay, trapezoid image. Sometimes it's called wide scanning. Wide scanning or trapezoid image is what? It's a different pattern of steering of the sound beam that will end up by bringing me this trapezoid face. So the trapezoid shape of the active elements here, okay, we're having here the near field is having the same width of the active element of the transducer, but the far field, excuse me, the far field is wider. So I'm getting here a wider far field. Why? Because there are one of two techniques. We need to know this. The trapezoid function of the active elements here, okay, or the trapezoid function of the image is achieved via one of two techniques. Either the outer elements, the outer segments of the trapezoid of the PZT, they are steered to the side. So the steering here, there is some kind of steering, which is the phasing. I will get the outer elements are steered to the sides, and that's why I will get the steering of the beam going fanning out. So the outer parts are fanning out. Okay. So this is one technique. The other technique is what we call spatial compounding or compound imaging. What happens with the compound imaging, I will get all the elements are steered in one direction. Okay, for example, let me make it the green one. For example, here, so I mean all the elements are arranged or steered in this direction, and then another frame that is formed by the same set of elements, but they are steered in the other direction. So we're getting here another pattern of scanning like this, right? And then I will get the center part is achieved rectangular. So I'm getting here three images, one straight down, or three frames, one straight down rectangular, one parallelogram to the right, one parallelogram to the left. Both, or all of these are compound together, and that's why we call it compound imaging, okay? So compound imaging or spatial compounding, I will get three frames are compound together to bring me one frame, and this frame will be the trapezoid frame. So this is again another way of attaining a trapezoid scanning, that when you get either the outer elements are steered to the outer side, so laterally, right and left, or the whole probe will get three frames, which are called the spatial compound. All right, so now I have two image shapes. We're having the rectangular and I have the trapezoid. What about the third pattern, which is called parallelogram? Parallelogram, I get the beam that all the active elements are steered to one direction. So I'm getting what we call the parallelogram. Okay. Sometimes this is used in some machines that are capable of doing this, that will help you to scan. For example, when you get the ICE and under the angle of the mandible, you can get the ICE a little bit further inside. Or if you have retrosternal goiter, sometimes you need to get the beam under the sternum a little bit. So this, it might help in scanning some of the parts that need an angled beam, okay, not straight down. So this is again, this is the linear array probe, right? Linear array sequential or linear array segmental probe. So we come to the other probe, which is the curvilinear, and the curvilinear here is having the active elements are arranged in the curved pattern. So it's a curved line. Okay, it's not straight line, curved line, and that's why sometimes it's called the convex or the curved probe, convex probe or curved probe, or the curvilinear probe. Sometimes people call it the abdominal probe, okay, because usually it's made or commonly used for abdominal scan. Okay, so the image shape looks what? We are all familiar with this, which is the blunt sector. The blunt sector here, we have the near field is curved and the far field is curved like here, but the near field is narrower and the far field is wider. And that's why it's used for abdominal scanning. Why I need to get deep part of the abdomen or the whatever abdomen or OB, I need to get the deep part wider scanning. And that's why we use it for abdomen or OB/GYN. So this is the widest far field. And also if you come to the near field, is the widest near field compared to what? Compared to the phase array. If you look to the phase array, the near field is a point, right? The near field is coming from a point. This is a sector probe. But this one here is a blunt sector. Okay, blunt sector is this curved arrangement of the active elements here that will bring me the near field a little bit wider compared to the near field in the phase array, which is the sector image. And that's why this is the one that is characterized by what? This blunt sector. The widest near field and the widest far field you can get is by the blunt sector probe or the curvilinear probe. So this is the widest possible near field and also widest possible far field. Okay, and that's why it's very familiar to be used for the abdominal scanning. Now, what if I'm having a kind of damage to the elements? Okay, again, this is the segmental. So they are in a segment. So like having, for example, a segment made of 10 or 15. Okay, let's assume that we have like 7 or 8 of these active elements are damaged, physically are damaged. For some reason or another, they are damaged. Okay, what happened now? This segment will lose its function. So I will get a dropout line that is vertical. So this is vertical dropout line that is coming from the face of the transducer all the way down to the end. Okay, this is characteristic of the active element damage. I will get here the dropout line starting from where? From the very top of the image, the face of the transducer. Okay, this is different. Okay, we need to know this in our mind. This is different from if I'm having, for example, a calcification or a whatever, a rib or whatever, something in the image. What happened? I'll get shadowing, right? So, but this shadowing, it starts from where? Starts from the rib or the stone, not starting from the face of the transducer, right? So this is here how to differentiate. The one that is starting from the face of the transducer is a dropout line because of some damage to the active elements, but the one is shadowing from a rib or a stone is coming from this particular part, which is the rib or the stone. That's why it's not coming from the face of the transducer, right? So this is sometimes you get an image that is having this shadowing and you tell, okay, this is, choose the reason of this shadowing. Is it dropout line or shadowing or what we call shadowing by attenuation? Okay, so we get, this is shadowing of attenuation, which starts from the stone or a rib. But if it's coming from the face of the transducer, this is a dropout line. Both conditions that happen here, the same will happen in the curvilinear, right? So we get a dropout line that is vertical. Applications. Okay, the linear probe, again, we know that because of the narrow field, both in the far field and the near field, they are both narrow because they are the same size of the transducer, which is usually like 3.5 centimeter, almost. Sometimes it's 5 centimeter, but it depends on the manufacturer that is applying all these active elements together. So again, we have the linear probe is having a narrow far field. So I can use it for deeper structures? No, I cannot use it for abdomen or OB. That's why, because it's a limited far field, I use it only in the superficial structures, okay? That I don't need to go wider in the deeper field. So superficial structure. And for this reason, because it's used for superficial structures, or because it's used also for vascular. So this is the reason why it is provided with high frequency elements. So the far field is narrow and it's provided with high frequency elements. Why? Because I don't need deeper. Okay, I'm not scanning deeper, I'm scanning shallower. That's why it's provided with high frequency elements, right? So it's used for small parts or vascular, and sometimes it's in the MSK, musculoskeletal also. Okay. The curvilinear, or the array transducer curvilinear, is used for abdomen on OBGYN because it has a wide far field, and that's why it's provided with lower frequency elements. Okay. And the only defect of this transducer is that sometimes the shoulders of this transducer will lose contact with the skin. That's why sometimes you will notice that by the edges of the image, right or left edges, okay, you must see some defect, lack of image, right? Because of what? There is a lack of skin contact. So this is the one that is like the only side effect, not the only, but one of the side effects or the drawbacks of this probe, that you might lose skin contact in the peripheral field. So this is here the how the trapezoid image is formed by the linear probe. I need to get some details about it or some more explanation here. Again, we have two techniques: either the lateral segments of the active elements, or the lateral segments, for example, 2 or 3 segments here, 2 or 3 segments here, will be steered outwards. So what will happen here? I'll get the scan lines coming out in this fan shape, and this will bring me the trapezoid shape. Okay, so this is not a separate transducer. I just want to emphasize this. The one that is having a trapezoid image is not a separate transducer. It is another application or another function for the linear array transducer. So again, one of the function is one of the ways is we get outward steering of the peripheral segments. Okay. The second method is, like we mentioned, spatial compounding. So I'm having here the active elements, and the whole active elements or the whole segment will form an image. So we have segments that each one will make a scan line in this direction. So finish this image or this frame, we'll start to make another image that is going straight down perpendicular, and then finishing this, the active elements, again all of them, will start to have another image parallelogram in the other direction. So we have two parallelograms and one rectangular image. If I add them, all of them together, I will get what we call the compound imaging or spatial compounding. Again, this is here some details about the trapezoid. Again, the trapezoid is not a separate transducer. It is application that is achieved by the linear array transducer. Thank you guys, and hope that was beneficial, and see you in the next transducer.